In the previous video, we started building the control logic for our computer, and we started by building a counter that counts through each step of our instruction cycle. Because each instruction that we want to define for our computer, whether it's load A, add, output, each of those instructions is made up of up to 5, or really it's always 5, although sometimes the last steps don't do anything, but it's 5 different microinstructions. And this counter counts through from 0 to 4 to keep track of which step we're on. And what we saw is that for T0 and T1, those first 2 steps of the microinstruction, those are always the same, regardless of which instruction we're actually trying to execute, because those 2 steps are the steps that fetched the instruction from memory and put it into the instruction register. And so in fact, we were able to sort of temporarily wire those up just by manually connecting these signals for T0 and T1 through an inverter to the appropriate logic signals here on the control word. But what I want to do in this video is replace this kind of temporary demonstration here for those first 2 steps with logic that's going to be able to carry out all of the steps for any instruction that we might want the computer to be able to do. And so in order to sort of understand how that's going to work, there's really kind of 2 pieces of information that feed into what control signals need to be active at any point in time. And one of those pieces of information is which step we're on here. So which of these time steps we're on. So, and that's what we're doing now. When we're on T0 or T1, we have signals that indicate that. But that's one piece of information. And so where we are in this count is one piece of information. But then the other piece of information, once we get into T2, T3, and T4, is going to be different based on which instruction we're actually executing. And so that piece of information is here in the instruction register, because by the time we get to T2, these first 2 steps will have loaded the appropriate instruction. So if the instruction is load A, that instruction is 0001, we'll have a 0001 sitting in the instruction register. So we have that information here. So all of the information we need in order to be able to set all of the control signals appropriately is available in a combination of what's in the instruction register plus where we are in our count, so where we are in the actual instruction cycle. So one way to look at what we've got so far for time T0 and T1, we're saying for T0 we're doing counter out and memory address register in, and that actually doesn't matter which instruction we're executing, because really at this point in the process we don't even know what instruction we're executing. We have to fetch it from memory first. So at T0 we're doing these things. So another way to look at that is kind of with a truth table here, where we say we have the instruction, which instruction is loaded, which is 4 bits, and then we have the step, which is 3 bits, and that counts from 0 to 4 in binary, because each instruction cycle is 5 clock cycles long. And so another way to kind of look at this is to say, well, regardless of what instruction, so we don't care what's in the instruction register, for step 0, we want to do counter out and memory address register in. So in other words, our control word over here is going to look like this. We're going to have a counter out, we're going to have that as a 1, and then memory address register in is also going to be a 1. And then the rest of these are all going to be zeros. And so that's what our control word looks like whenever we're at time T0 or at step 0, regardless of what instruction. So that's the same thing we're saying here. So T0, doesn't matter what instruction, those 2 bits are set. Now at time T1, we have these 3 bits set. So RAM out, so we're taking the contents of RAM, instruction register in, we're putting that contents into the instruction register, and then we're also incrementing the program counter, so counter enable. And so again, at time T1, we're at step 1 here, doesn't matter what instruction, because this is the same for every instruction that we're executing. In this case, we have RAM out is set to a 1, and then instruction register in is set to a 1, so we're moving contents from RAM into the instruction register, and then we're also incrementing the counter, so counter enabled is over here, that's the program counter. And then the rest of these are zeros. Got a little carried away and added an extra 0 there last time, but I forgot I left a little blank there. So this is essentially what we've got now, right? So step 0 we're doing this thing, and step 1 we're doing this other thing. So now where it gets interesting is at this point, after we've gone through these first 2 steps, the instruction register now actually has the instruction in it. And so for example, if our program here was load A 14, the instruction register, or the instruction for that is 0001. That's the instruction for load A, which we just made that up, but that's what we're saying load A is. And then the number, or the last 4 bits here is the operand for this, or it's a memory address location that we're loading data from into the A register. But what shows up in the first 4 bits of the instruction register is 0001. So in that case, we have 0001 in our instruction register for the next 3 steps. So that's going to be step 010, 011, and then 100. And then once this step counter here gets to 4, it resets back to 0, which we saw in the last video. And so now in this case, since we have 0001 in our instruction register, we know that we're going to be doing a load A, because that's load A. And so the steps for load A, which we talked about in a previous video, is we want to take the contents of the instruction register out and memory address register in. So we're essentially, if we're doing a load A14, we're moving that 14 into the memory address register so that we can fetch whatever is in that particular location in memory. And then in the next step, we do RAM out. So we take the contents of memory and put it into the A register in. So in other words, if our instruction register says 0001 and we're on step 2, 010, then we say instruction register out and memory address register in, and then everything else is zeros. And then for load A at time t3, we say RAM out, A register in. So RAM out, A register in, and the rest are zeros. And so that's everything for a load A command. We don't actually need to do anything at time t4. So in this case, we'll just leave all of the signals low, and that way, for that clock cycle, the computer won't do anything. Now the next instruction is add, and add, the opcode for that is 0010. And when that instruction is 0010, we do something different for times T2, T3, and T4. So this case here, this was load A, but for add, the instruction is going to be 0010, and it'll be 0010 for those last 3 steps of the instruction cycle. So this is the add command, and the way the add command works is, of course, we've already gone through, for step 0 and 1, we've fetched the add command from memory, and that's the same for every command. But then for steps, so 0, 1, 2, 3, and 4, for steps 2, 3, and 4 for the add command, the first thing we want to do is we want to take instruction register out and memory address register in. So we want to take the location. So if we're saying add 15, we want to go to memory address location 15 and get whatever is in there and add it to the A register. So add 15. So we take the instruction register out, we put that address into the memory address register, and then we take the contents of RAM, so RAM out, and put that into the B register, right? So B in is over here. And then that'll start to add whatever's in A and B. And so we take the sum out from that addition and put that back into the A register, so A in. And so these are the steps for the add command, and I'll just fill in the rest of these zeros. So that's the sequence of control signals that we want for the add command. And then the last command that we had in this program is the output command. And so the opcode for that, we decided was just going to be 1110. So we'll just do that here. That's 1110 will be the instruction that gets loaded if we want to use the output command. And again, that has the same 3 steps. And in this case, the output command is quite straightforward. It just takes the contents of the A register, so A out, and it puts it into the output register. So output register in is right here. And that's it. It only needs 1 more clock cycle. So these last 2 clock cycles are just unused. And you might be able to imagine some ways that you could optimize the computer to skip those in certain cases. But for now, we won't worry about that. So I'll just fill in the rest of these as all zeros. Now you might notice this is starting to look a lot like a truth table, where we have inputs over here on the left, which are the instruction register and the step that we're on. And then we have outputs, which are the control signals. And in fact, that's exactly what this is. This is a truth table that defines the logic that we need to build for the rest of the control logic. And so, you can imagine there's several ways we can build this. One is we could build this logic from discrete logic gates. So you could say, okay, well, these are my inputs. I've got 7 inputs and 15 outputs, and let me design a circuit using AND gates and OR gates and inverters NAND gates and all the rest that actually defines this logic. And you could do that. And if you go back and look at the video I did on building a 7-segment display decoder, I did something similar there. It was a bit less complex than this, and that got pretty complex. But you may also remember that we were able to simplify that by using an EEPROM. And in fact, if you look at this, you might think, well, this would be very easy to do with an EEPROM because you've got these 7 bits over here that are inputs, and you can imagine those being the address into a location in the EEPROM. And then these 15 bits over here, you can imagine being the contents that are stored in the EEPROM. And that's exactly what we're going to do with this computer. The problem, of course, is that the EEPROMs that we've been using are these 28C16 EEPROMs, and I'm going to continue to use those for the control logic as well. But you'll remember, they've got, 11 address lines going in here, and of course we only need 7. And there's only 8 data pins, so there's only sort of 8 outputs. And so as far as the address lines go, that's easy enough. We can just set the rest of them to zeros. As far as the outputs go, well, there's only 8 outputs, but we can use 2 chips to get 8 outputs from one and then 8 outputs from the other. And that's kind of why I've divided these like this, so that we'll have half of the control word in one of the chips and the other half of the control word in the other chip. And then as far as the instruction and step, those will be the address inputs to both chips. We'll just feed that into both of them. So now to actually build that, to add those EEPROMs into our circuit here, first I'm going to get rid of this sort of temporary setup that I had here with this inverter. We're not going to need that, since we're going to replace all that functionality with the EEPROMs. And I'm also going to disconnect all of these jumpers that I was using to manually set the control words, because we're now going to be able to use the control logic that we're about to build. So we'll get all that out of the way. So I add the EEPROMs here. And the first thing I'll do with each of these is just hook up power and ground. Now if we look at the pinout for these chips, there's a couple other things that we want to make sure we hook up. We've got the write enable, output enable, and chip enable, and we want to make sure each of those is set properly. So write enable, well, all of these are active low, and so we want write enable. We don't want to be writing to the chip. We only ever want to read from this once it's in the circuit here. So we want that to be high because we don't want to write. And then output enable and chip enable we want to be low because we do want the output enabled and we do want the chip enabled. So I'll set write enable high on both of these, and then output enable low, so that's active. And then chip enable is also low, so that's also active. Now the address lines for each of these chips is going to come from the instruction as well as the step, because those are kind of the inputs, if you will, to this truth table. So those are going to be the address lines. And so there's only 7 bits there for that address. And each of these chips has an 11-bit address. So we want to make sure that our address is going to come in here on A0 through A6, those first 7 bits of the address. But then A7, A8, A9, and A10, we're not going to use those. We just want to tie all of those to ground. So I'm just going to do that now. So A7 is down here, and then A8, A9, and A10 are all up here. So we'll just tie all of those to ground. And same thing for the second chip over here. So A7, A8, A9, and A10. And so now the only pins that aren't connected are A0 through A6, the 7 address lines, as well as the I/O lines, IO0 through IO7. And those are the signals that we want to use, right? So we have 7 address lines for our inputs, and then for each chip we've got 8 outputs. And actually here we're not using one of those, but that's okay. We might find a use for it later on. So what I'm going to do is I'm going to set up these as our address. So this will be A0, A1, A2, A3, A4, A5, and A6. So let me first hook up the step, those 3 bits, which are basically these 3 bits here that count which step we're on. Let me hook those up to the first 3 address lines. So let me just figure out which of these, I forget which of these 3 is the least significant bit, so which one should be address 0. So let me just double check. We add power. See, the clock's not running, probably because we're halted. So if I connect our halt signal, because I've disconnected that, if I connect that back to ground, there we go. So clock's running. So you can see this LED here on the left is the least significant bit, and that snakes around here, so that's this signal here. So if I hook that signal there to address 0, which, let's see, these 3 pins here are going to be the I/O pins, so that should be A0 there. And then this next one is A1 and A2. So there we go. I'll just disconnect that. So we've got the first 3 address bits hooked up to our which step we're on. So those 3 bits. And then the next 4 address lines are going to go to the instruction, which is this, these 4 bits here, whatever instruction we end up loading. And so there we've got the 4 bits from the instruction register that indicate which instruction we're executing, now connected to 4 of the address lines for this first EEPROM. And now as far as the second EEPROM, we want all the same address lines connected to it. So we just need to connect those exact same address lines in the exact same order over to the second EEPROM so that both of them will be pointed to the same address at the same time. And then we'll have 8 bits from this plus 8 bits from this, which will give us 16 bits that'll let us set whatever our control word needs to be. So we can just connect those 8 address lines straight across. There we go. It's a little bit tight in there, but hopefully that'll work. If not, we'll have something to troubleshoot. So next, we just need to hook up the I/O lines, which are, in this case, since we're not writing to this, they're just output lines. So we need to hook up the 8 output lines over to our control signals over here. And the way I want to do that is, I've got I/O 0 through 7. And I want to basically just kind of, to make things easy, line it up kind of in the same order that it is here, so that for the chip on the left will be these 8 bits on the left, the chip on the right will be these 8 bits on the right, and then the bit on the right here, this will be I/O 0 and I/O 1, 2, 3, 4, 5, 6, 7, and then over here this will actually be I/O 1. We won't use 0. 1, 2, 3, 4, 5, 6, 7 will be the sum out. Just to kind of keep things in order. And again, you can do it any order you want, but you just have to kind of keep track of things. So I'm just going to do it kind of in the way that it's laid out here, just to preserve my sanity. And so that means halt, which is over here on the left, is going to be D7, or I/O 7, I guess. I/O 7 on the chip on the left. So I/O 7 is this pin here. So I want to connect that over to halt. So that's this pin here. And then I want to connect that to my halt signal here. And then just go down the line here. So I/O 6 is going to connect to the next signal, which is memory in. I/O 5 is going to go to RAM in. I/O 4 is going to RAM out. And I/O 3 is going to instruction register out. And then I/O 2 is down here next to ground. And that's going over to instruction register in. I/O 1 is going to A register in. And finally I/O 0 is going to A register out. And so that's the first 8 of those control signals is hooked up to the 8 bits from the first EEPROM. And so now I'll just do the same thing for the second EEPROM. So again, we're going to start with I/O 7, which will go to the sum out signal. So I/O 7 is here, and that'll go to sum out. I/O 6 goes to subtract. I/O 5 goes to B in. I/O 4 goes to output register in. And I/O 3 over here goes to counter enable. Get all those in there. Nice jumbled mess. And then I/O 2 down here comes around to counter out. And then finally I/O 1 goes to jump. And then I/O 0 is not connected for now. But we could add another signal over here, and that would be I/O 0. And actually I left room over here and over here to add another EEPROM and some more LEDs if we want to add even more control signals to expand what the computer can do maybe in the future. And so now we've basically hooked this up so that our instruction and what step we're on control, or can control, I suppose, the control signals over here. But of course we need to actually program the EEPROMs before it'll actually do what we want. Now, I built this Arduino EEPROM programmer in a previous video, and I would normally use that, I think, if once the computer gets a bit more complicated, we want to program a bunch of instructions into it. But for now, I think it's going to be a little bit clearer to see what's going on if I use this manual EEPROM programmer that we also built in a previous video. So I'm going to pull out this first EEPROM and stick it in here. Make sure it's in the right place. And if we power this up, let's see, we've got all ones in there. But we want to start writing to this EEPROM. So I go into write mode here, and basically what we want to do is write in this data. Essentially in each of these addresses, we want to write the appropriate data, this here. So this is the EEPROM on the left that we're programming now. So the first thing I want to do is program in for step 0. And so step 0 is where these first 3 bits of the address on the left are all 0, 0, 0, 0. And then we don't care what the instruction is. So it doesn't matter what these next 4 bits are. They can be anything. We want to program in this particular 8-bit value here. And really what that 8-bit value is it's setting, we can actually use the same label here, it's setting the memory in and then the counter out. So counter out is over here, that's on the other EEPROM. So for this EEPROM, it's step 0. Really all we need to program is memory in. We want to set that high. So let me set that high. There's memory in. And then the rest of the bits will set low. So I'll just tie them all to ground. And so I'll program this at address 0 by pushing that button. And so that sets it for step 0 for instruction 0, but we want it for any instruction. So really what I want to do is cycle through all of the possible instructions. So I'll go to instruction 1, step 0, and program that in. And then I'll go to instruction 2, step 0, and program that in. And instruction 3, and program it in. And then instruction 4, and program it in. Instruction 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So now for every possible combination of instruction bits here, so all 16 possible instructions for step 0, I've programmed in this memory in bit high and then the rest of these bits low. So that handles this case here. So the next case is step 1. And so step 1 for any instruction, we want RAM out and instruction register in. So let me set those bits. So RAM out is going to be that bit, and instruction register in is that bit. So 000101000, 000101000. So that's what we want set for step 1. Again, any instruction. So I'll set that for instruction 0, and then I'll just cycle through the remaining 15 instructions and set it for each of them, just like we did with the last step. Okay, so now for step 1, all 16 instructions, any combination of instruction bits, we've now set this RAM out, instruction register in, like that. Now we can come on to the actual microcode for each instruction. So for load A, that one is going to be, in this case, step 2, right? And then load A is 0001. So now we have this instruction, step 2, is going to be, see, memory address register in, instruction register out. So let's set that. And so we'll program that. And then the next step is, again, instruction 1, step 3. So we'll set step 3 here. So instruction 1, step 3. And we'll set here, we want RAM out and A register in. And we'll program that. And then finally step 4 is actually just all zeros. So we'll program that. So now we program the microcode for the load A command. So next we've got the add command. And so add command is 0010 is the opcode for the add command. And then we'll go back to step 2. And so for step 2, instruction register out, memory address register in, that sounds right. Program that. Next step, that's RAM out. And then we're also going to do, it looks like, B in. Yep, that makes sense, but that's over here on the other chip, so we're not programming that yet. So we'll program that. And then we go to step 4 for the add command. So we got add command step 4. And in that case, on this side, we just have the A in. That's A in is high, and we'll program that. So that's the add command. And then the output command, the opcode for that is 1110. And then we'll go back to step 2. And we just have A out. So we got A out. We'll program that. And then step 3, all zeros, program that. And step 4 is also all zeros, so we'll program that. And so now this EEPROM is completely programmed for the fetch cycle for any instruction, as well as the additional microcode instructions for load A, add, and the output commands. So now we can pop this out and put it back in the computer. And then we'll pull out the next one and program that one the same way. So if we put this in here now, we'll go back to address 0. And this time around, we're over here programming those bits of the control word. And so again, we have to program the fetch. So in this case, we're programming this side over here. So for step 0, we want the counter out to be enabled, and that's now this bit here is counter out. And just like before, we want to program step 0 for counter out into all of the different instructions. So we'll just cycle through instruction 0 through 15. Okay, and so now we have that counter out bit set for all of step 0. And we'll do the same thing for step 1, where we want the counter enable to be set. So counter enable set for step 1, and again, we'll cycle through all of the different instructions, because we don't know what's going to be in the instruction register for the first 2 steps of the instruction cycle. So there we go. I think I've got all those programmed correctly. And so then moving on to step 2, we get into each of the different instructions. And so I'll go ahead and program the same thing for, or program the correct thing, I should say, for each of the instructions here. So load A can be all zeros, and then add, and then finally, for output, we want output enable thing. Okay, so now the second EEPROM is programmed, so we'll go ahead and put that back in the computer as well. All right, so now with these programmed, we should have the fetch cycle working just like we did before, but now it's part of the EEPROM. And as well as the load A, add, and output commands should all hopefully work. But let's test it out. So if we go ahead and connect power, hard to say what's going to happen here, but if we just stop the clock for now, and go ahead into programming mode, and let's go and program this program back into memory so that we know what's in memory and we can step through and see if it works the way that we think it will. So this program, again, is just going to do a load A 14, add 15, and then output. So load A 14, we'll go to address 0 and put in that load A 14. So load A 14, and then address 1 will be add 15, so add is 0010, and then 15 is all ones, so add 15, and then we go to address 2, and we want to do output. Opcode for that is 1110, and then the rest of it we don't care. So that's output. And then we just need to put our data, right, because we've got data in address 14 and 15 that we're loading and then adding. And so that's a 28 and a 40, or 14. So in address 14, we want to put that 28, so that's 000, 111, 00. There's our 28. And then we'll go to address 15, and we want to put in a 14 there, so 1110. So there we go. Yep. And if we go back into program mode, we can start to try to step through our program. And so first thing I'll do is just kind of reset everything. So you see our program counter is at this weird value, but I can just reset that. And then our A register, B register is all 0. Everything else seems to be all 0. We're on T0 here. So I think we're ready to, we'll run the program, but I'm going to single step through just to make sure that everything is working the way that we hope it would. So we're at time T0 here, so step 0, and it doesn't matter what our instruction is. In this case, it's all zeros, but that's fine. So step 0, we want to do a, counter out and memory address register in, and so counter is 0, and we're going to put that into the memory address register. So counter out, memory address register in, so we do that. Nothing really happens. We're just putting a 0 there. But now we're at time T1, and so step 1 here, again, doesn't matter what our instruction is. We're going to do RAM out, instruction register in, and counter enable. And so we've got RAM out, instruction register in, and counter enable. So it's going to take the contents of RAM, put it into the instruction register, and then also increment our counter. So we'll go ahead and single step that with the clock. and there it is. So that moves that there, and our counter is now 1. So now at this point, we're on time t2, so 0, 1, 0 is the step we're on. And now it actually matters what our instruction is. And so our instruction is 0001, which is the opcode for load A. And so with that opcode on step 010, then our EEPROMs should be outputting, it looks like instruction register out and memory address register in, and that's exactly what we've got here. So that looks like it's working well, and so that's going to take the contents of the instruction register, or at least the lower 4 bits, and put that into the memory address register. So we'll single step that, and there it is. There's our 14 there. And now we're on time t3, so we're 011 is our step, and then our instruction is still the load A instruction here. And so now we should be doing a RAM out and A register in. So indeed, that's what we've got, RAM out, A in. So it should take the contents of RAM and put it over in the A register. So we'll advance the clock, and that's what happens. Puts that 28 over there into the A register. And then now we're on step 100, and our instruction is still load A, 0001. And we're done with the load A. We've loaded that 28 into the A register, so we don't need to do anything. So this step basically doesn't do anything. So there's nothing set here. So it's really just kind of a waste of time, if you will. But maybe there's a way to optimize that in the future. But for now, it's okay. We'll just use an extra clock cycle to advance the clock, and nothing will happen. But we go back to time t0. And so now we're back at time t0. So we're at step 0. Our instruction is different now, though, right? It's before we had instruction 0 in here, which we haven't really defined. Now we have instruction 1, but it doesn't matter, right? Because we programmed this step 0 for every instruction. So we're still going to do the same thing. We're still going to do the counter out and the memory address register in. But now this time the counter is 1. So we're going to put a 1 into the memory address register, which will now get the next instruction, which is add 15. That's what we programmed into address 1. And so now we're at time 2, and again, or excuse me, time 1, T1, so 001. And again, it doesn't matter what our instruction is, we're still going to do this RAM out, instruction register in, and counter enable. And so that's what we have here. So we've got our EEPROMs programmed correctly. And so we'll see the RAM out, so we'll see this contents here move into the instruction register, and then also the counter incremented here. So now our instruction register, we've got 0010, and that's the opcode for add. So now we're on step 2, 010, but instead of 010 and having the load A command here, we've got 010, and we now have the add command here in our instruction register. And so we're going to do something different. So here, this time we're going to do, let's see, we're going to do instruction register out and memory address register in. And so that appears to be what's showing up here. So we got the EEPROM programmed right. So it's going to take, again, this address from the instruction register and move it into the memory address register. So now we can get at the contents of memory, which is this 14. So the next step here, we're 011 is the step we're on. We're still doing an add, because that's what's in our instruction register. So we've got RAM out and B in, and indeed that's what's showing up down here. So RAM out, B in, so it's going to put this 14 into the B register. And that's what it does. And now we've got the 28 in A and the 14 in B, so we get the sum over here. And so the add is then going to take the sum out, take this sum out and put it into the A register. And so that's in fact what we have here. And of course, it latches that into the A register just immediately on the rising edge of the clock. So as soon as that goes in here, it'll latch. And then, of course, now the new sum is there, but we've only latched it into the A register, so we have the sum of those values. And that actually used up all of our clock cycles for our instruction cycle, and so we're back at instruction 0 again. But now, our instruction is still saying add, but we don't care. We're in step 0, so we don't care what the instruction is. We're going to fetch the next instruction. So we've got counter out, memory address register in again. So we're going to put our 2 over here, because we want to fetch the next instruction from address 2, which we programmed as the out command. So we've got that, and then we're going to do step 1, which is RAM out. So the contents of RAM, which is the got our instruction in it. We're going to put that in the instruction register, and we're also going to increment our counter. And what happened? Something didn't work right, and I didn't see what happened. This should be at address 2. I'm not sure why that went to 0. We've got a load A here, and so it's saying instruction out, memory address register in, which is right, but I don't know why we have a load A there. We should have done something different. And I'm not sure what happened. So what I'm going to do, since I didn't see what happened, is try to set that up again. So we have the program still in memory. So I'm actually going to reset everything. I'm going to reset the program counter to 0. I'm going to reset the A register to 0. I'm going to reset the B register to 0. I'm going to reset the instruction register to 0. And I'm going to reset, let's see, how do I reset you? Probably just going to have to advance the clock until we get to T0. Okay, there we are. So that's a T0, program counter, make sure that's back at 0. Okay, so we're reset, and I'm actually just going to step through because the place we failed was in loading the output. So let me do the load A and the add. So I'm going to just quickly step through the load A again. So it's the first 5. So that did a load A, and we've got our 28 there. The next 5 clock cycles, we'll do the add. And we've got our sum now is in the A register. And so we're kind of back where things went awry. And so let me just look at this and make sure things make sense. So we're at T0. We just did our add. And we're saying counter out, memory address register in. So the 2 is going to go to the memory address register. So there it is. And here is our output command. It's in memory. And the next thing we want to do is we want to say RAM out, instruction register in, counter enable. So we've got RAM out, instruction register in, counter enable. So this should put, and this is the step where it didn't work last time, so I'm suspicious, but this should put this 1110 into the instruction register, and then increment the program counter to 3. So let me just run the clock one step, and that time it worked. We have the right instruction here. So maybe I bumped something. That is the problem with breadboards, is sometimes things are loose and unreliable. So it might be I bumped something, but it looks like this time it worked. So we're back here. We've just loaded. We're at step T2 now, and we have the output command in our instruction register. And so now what we're going to do is we're going to say A out and output register in, and that's what we've got here. And so if we step this, it should take the contents of the A register and display it on the output. And there it is, 42 is the answer, as it should be. And the next 2 parts of output are just all zeros. So we've got all zeros, so that's a clock cycle, and then all zeros, that's a clock cycle, and we're back to T0 again. And of course, we didn't program anything in after these 3 commands, so there's just garbage in memory. So if I keep running it, who knows what'll happen. But it looks like that one little anomaly, and I'm going to guess that I bumped something. Maybe when I watch back over the video, I'll notice that I bumped something or something like that, hopefully. But it looks like we've got these commands working: the load A, the add, the output. We were able to program them in memory and then run the program. And just for fun, instead of single stepping it, let's try to run the program automatically. So what I'll do is reset everything. So I'll reset our program counter, reset the A register, reset the B register, reset the output register to 0, reset the program or the instruction register, and we'll reset the memory address register as well. So everything is set to 0. We're on T0 here. If I start the clock, it should run those commands and output the result, and it's going to keep running, so who knows what it'll do after it outputs the result, but it should at least output that result. So let's give it a go. And there it is, and then you saw the 42, but then who knows what it's doing now. So maybe what we really want is we want a halt command, so maybe that'll be the next command we add next is a halt. And let's say that's going to go in address 0011. And we get to make up the opcode we want for it. So let's just say it's going to be 1111, and then it doesn't have any parameter there. So if we want to make a halt command, we actually can do that. We just need to program in the right microcode into our EEPROMs to add this halt command. So let me stop this for now. And so if we want to add a halt command here, we've got 1111 is going to be the opcode for it. And of course, it's still going to have the same 3 steps. Although, as you'll see, it'll never actually get to the other 2 because it's going to halt the computer. But basically, this is a simple enough command because we have a halt signal. And remember, if this halt signal goes high, the clock stops. So if we just set that high, it doesn't really matter what else we do. The clock will stop, and that'll be that. The computer will stop until we reset it somehow. So this will be the halt command. And this should be a pretty easy thing to program into our 2 EEPROMs. So yeah, let's do that real quick. So if you want to program that in, here's the left EEPROM. And here we want to go to halt, which is 1111. And then step 2, we want to program here. We want to set this first pin low, or high, excuse me, and then everything else low. And program that. And then for step 3, we'll just do all zeros, and step 4, all zeros. And then the left one, we just want to make sure we've got all zeros in it. So here, program all zeros. So we've got halt, and then so for 2, 3, and 4, we want to put zeros in there. So I just pulled those EEPROMs out and reprogrammed the halt command without shutting the rest of the computer, without pulling power off the computer. Just pulled the chips out and put them back in. So the program should still be in memory, but let's just walk through and make sure, and then also add that halt command to it. So at address 0, we've got our load A 14. At address 1, we still have our add 15. At address 2, we've got our output. And then address 3, we've got garbage, but what I want to do is put a halt command there, which we now have. And so that's a halt. So that should be there. And then let's just double check address 14 and 15 still have our data. That's good. Go back into run mode. Make sure everything's reset. So we're at time T0, so that's good. Program counter, A register, B register, instruction register, all zeros. I guess memory address register, we could reset that as well to 0, although it doesn't matter. The first thing to do is to take our memory address register, or counter out and memory address register in. But I think that should be it. And so in theory, if we just run this program, it'll do that load A, add 15, output the result, and then halt the clock. And so we should see this halt light come on, and we should see the clock stop. So let's let her rip. And there it goes. We got our 42 output, and then we got our halt here, and the computer is halted. So it ran through the load A14, it added the 15, we outputted the result, and then it halted. And so we also were able to just add that new halt command just like that. So I'm going to leave it there for now. In the next video, we'll probably go through adding some more commands and just making the computer more capable by adding new instructions to it.